Welcome to this class, and today we'll solve some numerical problems on gas laws and specific heats. So we have to use some formulas related to this. For example, we have to use the formula for equation for characteristic gas equation. This is PV equal to mRT, where m is the mass of the gas, r is the characteristic gas constant, T is temperature in absolute scale, and P and V are respectively the pressure and volume. And this formula can also be used in this form: P1 V1 by T1 is equal to P2 V2 by T2. Also, we'll use the relation between Cp and Cv, which is Cp minus Cv equal to R. Cp is specific heat capacity at constant pressure, and Cv is specific heat capacity at constant volume. And also we will use the formula for amount of heat transfer during a process 1-2 is equal to m Cv T2 minus T1. This is for a constant volume process, and if the process is constant pressure process, then the formula will be m Cp T2 minus T1, and Cp is the Cp for constant pressure process and Cv is for constant volume process. And above and all this, we will also use the formula for change in internal energy and also for amount of work done. So let us solve a simple problem. A closed vessel means, since it is a closed vessel, the volume cannot change. So this will be a constant volume process. And the vessel contains 3 kg of carbon dioxide gas at a temperature of 27 degree and pressure 0.7 bar. The heat supplied to the vessel, we have to find out. It is supplied until the gas pressure increases to 1.5 bar. So because of the heat addition, the pressure increases. We are to calculate the value of the heat supplied. And in a constant volume process, volume cannot change, but due to the heat addition, not only the pressure will increase, also the temperature will increase. And for solution of this problem, the specific capacity of carbon dioxide at constant volume is given. This is the Cv value. And we can represent this in a temperature volume diagram like this. So the volume does not change, that means V1 equal to V2, and pressure changes from P1 to P2, and the process is 1-2. Similarly, the diagram for PV would be like this, and the previous one is, this is T1 and T2. In this case, it will be P1 and P2. This is pressure volume, and this one was actually temperature volume diagram. And the process is 1-2. In this problem, we have to solve the problem. The given data are like this. It is a closed vessel, so volume remain constant. So V1 equal to V2. Also, the mass of the gas is 3 kg. The vessel contains 3 kg of carbon dioxide gas. Initial temperature is T1, which is 27 degree. We convert it to Kelvin. 27 plus 273, 300 degree Kelvin. And initial pressure is P1, which is 0.7 bar, or we can convert it to 0.7 into 10 to the power 5 Newton per meter square. If necessary, we have to convert it to Newton per meter square. Let's see what we have to do. We can consider bar also in this problem. And final pressure increases to 1.5 bar, and at the same time the specific heat at constant volume Cv is given 0.846 kilojoule per kg per Kelvin. So we have to find out the amount of heat supplied Qs in this process. So the amount of heat supplied, the formula is mCv T2 minus T1. So m is given, Cv is given, initial temperature T1 is also given in the problem, but T2 temperature is not given. So for the process 1-2, which is a constant volume process, we can apply one law. We can apply characteristic gas equation at point 1 and 2, and this will give us a relation like this: P2V2 divided by T2 equal to P1V1 by T1. Since the volume V2 is equal to V1, so the relation becomes P2 by T2 is equal to P1 by T2. And this is actually Charles' law. At constant volume, pressure is directly proportional to temperature. So from this relation, we have to find out temperature T2. T2 is equal to P2 upon P1 multiplied by T1, and P2 is given 1.5 bar and P1 is 0.7 bar multiplied by the temperature, which is equal to 300 Kelvin. So it will, temperature will get in Kelvin. Temperature T1 is equal to 27 degrees centigrade, that means 300 degree Kelvin. So if we calculate this, so it will come out to be 642.7 approximately this much of Kelvin. So we have found out the temperature, final temperature. That means T2 we have found out, T1 is given, and we have to find out the heat supplied. So now we can calculate the amount of heat supplied, Qs equal to mCv T2 minus T1. So simply put the values: m is equal to 3 kg, Cv is equal to 0.846 multiplied by temperature, which is equal, temperature difference is equal to 642.7 minus 300, and it will come out as kilojoule. We will get in kilojoule, and this is equal to approximately 870.3 kilojoule. So this is the solution of the problem. This is a very simple and easy problem. Okay, so next let us solve another problem. Just study the problem. A gas contained in a closed vessel. So this is also a constant volume process. Closed vessel is having initial pressure and temperature 20 bar absolute and 50 degrees centigrade respectively. If it is heated to 120 degrees centigrade, so in this problem final temperature is given, then we have to find out the final pressure. So these are the values. Initial pressure P1 is equal to 20 bar. It is 20 into 10 to the power 5 Newton per meter square. Again, initial temperature T1 is equal to 50 degrees centigrade, which is equal to 323 Kelvin. Final temperature T2 is equal to 120 degrees centigrade, so it is 393 Kelvin. We have to find the final pressure P2. So as usual, we can apply characteristic gas equation, or also we can apply Charles' law directly. From this also we will get this, because P1 equal to V2. So from this we will do the calculation. Now P2 is equal to from here we will get this one, T2 upon T1 multiplied by P1. So temperature is 393 divided by 323 multiplied by pressure is 20 bar. If we put in bar, then we will get in the bar itself, and this is after calculation we will get it 24.33 bar. So the previous one was on temperature was unknown, final temperature, and in this problem the final pressure is unknown. So that is the solution of the problem. Now problem number 3. Let us study the problem. 1 kg of ideal gas is heated from 18.3 degrees centigrade to 93.4 degrees centigrade. Assume R is equal to 26.9 kg force meter per kg per Kelvin and gamma equal to 1.18 for the gas. We have to find out specific heat, change in internal energy, and change in enthalpy. So the given data are mass of the gas equal to 1 kg, initial temperature equal to T1 18.3 plus 273, that is 291.3 degree Kelvin, and final temperature T2 is equal to 93.4, that means 366.4 degree Kelvin. And also the characteristic gas constant R is 26.9 kg force meter per kg per Kelvin, and ratio of specific heat gamma is equal to 1.8, and this is equal to actually Cp divided by Cv. Ratio of specific heats is called gamma. Now this problem is in metric unit, that is why these values are not in kilojoule or joule, but it is in kg force meter. So let us solve this problem in metric unit itself. So to find out heat at constant pressure, specific heats, and that means we have to find out Cp as well as Cv. Also change in internal energy U2 minus U1, and change in enthalpy H2 minus H1, that is equal to mCp T2 minus T1. So we have a relation between the Cp and Cv with R, and that is Cp minus Cv is equal to R. If we divide both sides by Cv, then this equation is like this: Cp minus Cv divided by Cv equal to this one. So by simplifying this, Cp by Cv minus 1 equal to R by Cv. But Cp minus Cv is equal to gamma. So we can write it like this: gamma minus 1 equal to this one. So we get the value of Cv as R divided by gamma minus 1, not value. The relation for Cv is R divided by gamma minus 1. So let us calculate the value of Cv, because R value of R is given, that is 26.9 divided by gamma is 1.18 minus 1. So this is equal to 149.4, and the unit will be kg force meter per kg per Kelvin. So we get the value of Cv. Now we can get the value of Cp also, because Cp minus Cv is equal to R. We can also use this value Cp divided by Cv equal to gamma, and from this you will get the Cp is equal to Cv plus R, and Cv is 149.4 plus R is equal to 26.9. So this will be is equal to 176.34 kg force meter per kg per kg per Kelvin. So this way we have find out both Cp and Cv. So this part is completed. Now we have to find out change in internal energy as well as change in enthalpy. Change in internal energy, U2 minus U1, U2 minus U1, change in internal energy, this is the part 2, second part, is equal to M Cv T2 minus T1. So you can put the values. M equal to 1 into Cv is 149.4 multiplied by 366.4 minus 291.3, and it will be equal to about 19.94 kg force meter. So this is equal to this much. Now third part of the problem, that is change in enthalpy H2 minus H1 is equal to mCp T2 minus T1. So M equal to 1, Cp is 176.34 multiplied by again 366.4 minus 291.3. So this will be is equal to 1324.134 kg force meter is the change in enthalpy. So since this problem is in metric unit, we can also convert this internal energy to heat unit. This is actually is in work unit, because in metric unit Q is equal to W by J, where J is the heat equivalent of work and value of J is 427, and by dividing W, that means work unit with by 427 we get in kilocalorie. So if we divide this quantity by 427, then it will be equal to 26.28 kilocalorie, that is heat unit. And in this case, if we divide it by 427, then it will be equal to 31.01 kilocalorie. So in SI unit it would be kilojoule, but in MKS unit or metric unit it is kilocalorie. So we have calculated specific heat of gas, Cp and Cv, change in internal energy, and also the enthalpy of the change in enthalpy during this process, heat addition process. A Carnot engine does 37 kg force meter of work per cycle while receiving 0.26 kilocalorie of heat at 260 degrees centigrade. Determine the temperature of sink at which the heat is rejected and the thermal efficiency of the engine. So first let us understand the problem. This is on Carnot engine, this is the Carnot engine. It receives Q1 quantity of heat from source at high temperature T1 equal to 260 degrees centigrade, and the part of this heat is converted to work, which we would say W net, and the rest amount of heat Q2 is rejected to the sink at a temperature lower temperature T2, and T2 is not given. The given data in this problem are: work done, W net is equal to 27 kg force meter. So this problem is also on metric units, metric system, and heat supplied is Q1 0.26 kilocalorie. So you can see that the units are not same, but we need to use same unit. If we convert this kilocalorie to kg force meter, then it will be 0.26 multiplied by 427. This is the conversion factor to convert it to kg force meter. If the unit should be same, then it will be approximately equal to 111 kg force meter. So this is the amount of heat supplied. Now source temperature, that means higher temperature, is T1 is equal to 260 degree, or you can say 533 Kelvin. So from this we can find out the efficiency. We have to find out efficiency as well as the sink temperature. It will be actually T2. Sink temperature T2 we have to find out. T1 is the higher temperature, T2 is the lower temperature. So first let us find out the efficiency. So efficiency of Carnot engine is equal to W net, that means work output, divided by QUS, that is heat input. So since we have converted to the same unit, W net is equal to 27 kg force meter, and QS, heat supplied in same unit, is equal to 111 kg force meter. We can convert both to kilocalorie also. 27 kg force, we can convert it by dividing 27 by 427, then we will get into kilocalorie. So this is equal to 27 divided by 427 kilocalorie. So this is equal to, efficiency is equal to 0.243, or you can say 24.3%. The efficiency of Carnot engine is 24.3%. Now we have to find out the sink temperature T2. So for sink temperature, again we will use the formula for efficiency of the Carnot engine, but this time we will use the formula on the basis of temperature. Say for this is T1 minus T2 divided by T1, where T1 is the temperature of the source, higher temperature, and T2 is the temperature of the sink, lower temperature. So if we put the values, efficiency already we have calculated 2.243, and temperature T1 is given in the problem, that is equal to 533 Kelvin minus T2 divided by 533. So by solving this we will get 0.243 multiplied by 533 is equal to 533 minus T2. Or we can say T2 is equal to 533 minus 0.243 multiplied by 533, and this is equal to temperature T2 is equal to that is 403.48 Kelvin. Remember, this temperature will get in Kelvin only, because this relation is on the temperature should be on Kelvin scale only, and this is also given in Kelvin, but we can convert it to in the centigrade, that is we can convert this to degree centigrade, that is 0.48 minus 273, and this way the problem is solved for all the required calculations, that is efficiency and temperature of the sink. Now the problem number 5, let's study this. 1 kg of air is expanded at a constant pressure. So whenever it is said that expanded at constant pressure, that means the process is constant pressure process. Expanded at 3 bar pressure from a volume of 0.3 meter cube to a volume of 0.5 meter cube. So volume changes from V1 to V2, 0.3 to 0.5. Pressure remain constant in 3 bar. We have to find out external work done, W, internal energy, change in internal energy of the gas, and the heat transferred during the process, and the value of R, characteristic gas constant, and specific heat at constant volume is given. So given data are M, mass of air M is equal to 1 kg. Then value of R is 287 joule per kg per Kelvin, or we can put it in kilojoule, 2.287 kilojoule per kg per Kelvin, and CV is given 0.72 kilojoule per kg per Kelvin. Again, the volume changes from V1 to V2. So V1 is equal to 0.3 meter cube and V2 is equal to 0.5 meter cube. Pressure P1 is equal to P2, that means constant pressure process, which is equal to 3 bar, or 3 bar is equal to, we can write 3 into 10 to the power 5 Newton per meter square. So in this problem we need to find out the value of Cp also. So from this relation Cp minus Cv equal to R, we'll try to find out Cp, which is equal to Cv plus R. So Cv equal to 0.72 and R is equal to 0.287 in same unit, kilojoule per second, kilojoule per kg per Kelvin, and that is equal to 1.007 kilojoule per kg per Kelvin. So we have found out the value of Cp, which will be required in the later stage. And also in this problem, temperature T1 is not given. Also temperature T2 is also not given. So from this formula we can find out the temperature T1. Say at point 1, say P1 V1 equal to M R T1, gas characteristic gas constant at point 1, where P1 equal to P2, that is equal to 3 bar. So we'll use this to find out the value of T1. So T1 is equal to P1 V1 divided by MR. So put the values. P is equal to pressure 3 into 10 to the power 2 that is 3 bar. 3 bar is equal to 3 into 10 to the power 5 Newton per meter square, and that is equal to 3 into 10 to the power 2 10 square kilo Newton per meter square. We put the value in kilonewton, and that multiplied by volume 0.3 meter cube, and this is in Newton per meter square, kilonewton per meter square, divided by m, which is mass of air in kg. 1 multiplied by r is equal to 0.287 kilojoule per kg per Kelvin. So all the units will be cancelled and only joule will be there, Kelvin will be there. And so temperature will be equal to 313.6 Kelvin. So temperature at point 1 is equal to 313.6 Kelvin. Also in this problem we have to find out the temperature T2. So for that temperature T2 also we can use the same formula at point 2. P2 V2 is equal to mR T2. So T2 is equal to P2 V2 divided by mR. So P2, pressure at point 2 is, so this is equal to pressure, same 3 into 10 to the power 2 multiplied by volume 0.5 meter cube, and divided by m equal to 1, r is equal to 0.287. So this will be is equal to 522.7 Kelvin. So both the temperature T1 and T1 are found out. So now we can calculate the three things. Number one is, we'll calculate external work done by the gas during the process 1-2. So W12 is the work done during the process. W12 is equal to, we can use the formula P V2 minus V1. We can also use the formula mR T2 minus T1. So any formula will do because we know all the values. So first one we will calculate using the first one. So P is equal to 3 into 10 square, and V2 is 0.5 minus V1, that is 0.3. So this will be is equal to 60 kilojoule. So work done during the process is 60 kilojoule. So next one is we have to find out change in internal energy. That means change in internal energy. Change in internal energy we will find out, and that is equal to U2 minus U1, and the formula is mCV T2 minus T1. So m is 1 kg mass, and CV, value of CV is 0.72. Temperatures are 22.7 minus temperature T1, which was equal to 313.6. So after calculation we will get it to be 150.6. So 150.6 kilojoule. So this is calculated. Now let's do the third part, which is the heat transferred during the process. So heat transferred during the process, that is Q12 is equal to the formula. This remember, this is a constant pressure process. So for constant pressure process, the heat transfer is equal to mCp, not Cp, mCp T2 minus T1. So we put the values m1 into m is 1, Cp is 1.007 multiplied by temperature difference 522.6 minus 313.6. so this will be is equal to approximately 210.6 kilojoule. So in this whole calculation, you can see W1, the change in internal energy, that we also can say du, and this is delta W, say, and amount of heat transfer is equal to delta Q. So first law of thermodynamics is delta Q is equal to du plus delta W. So if we put 200 and delta Q equal to 210.6 is equal to du, which is equal to 150.6 plus dW is equal to 60. So this way, this problem itself, it proves that the first law of thermodynamics is true for such a system. So this is first law of thermodynamics. The amount of 210.6 kilojoule of heat supplied to the system, a part of it is converted to work, which is 60. Out of that, 60 kilojoule is converted to work, and rest 150.6. This amount of heat is stored in the form of internal energy within the system. So that is first law of thermodynamics. So I think you can solve the problems like this, any kind of problem. These are very simple, but you should know the basic formulas and the principles. First law of thermodynamics, characteristic gas equations, the relation between Cp and Cv, and so on.